And it's it's a massive area where the south side of Mammoth Mountain, over 170 acres, carbon dioxide levels, Jesse, were over 90%.
Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Well, Chris, I'd say let's get into it because this is going to be a little bit of a longer discussion, I think, in part because it's a really interesting juxtaposition. We're focusing here on the Long Valley Caldera, the hydrothermal features and the hydrothermal activity in the Long Valley Caldera, but we have a lot of. This is where I think the analogies with with Yellowstone are the closest, but again, they don't map on perfectly. There's some key differences here, right? Is that fair?
Yeah, but I think that that's a good thing to bring in. You know, there's a lot of hydrothermal activity at Long Valley Caldera, but it's different than what it looks like in Yellowstone, and there are reasons for that.
Very different.
That's what I'm looking forward to, pointing out. Why?
Yeah.
Yellowstone has all these geysers, and yet Long Valley has seemingly all of the makings for that same thing, but they don't. Yeah, it's an interesting thing.
Yeah, interesting combination here. I think, Chris, that just to frame it again, this is a part of our series on Long Valley Caldera. We're going to continue using the Long Valley Caldera system and geology of that region to kind of focus in on the first principles of different topics because it's such a rich and complicated story there. And this one's going to be the hydrothermal activity, hot springs, geysers, fumaroles, and some interesting story about volcanic degassing, which will lead us nicely into the last chapter that we're going to talk about next episode. Next chapter is going to be about kind of the geology underfoot, like what's going on under volcanoes, how do we monitor this, what are some of the ideas. But this one's focusing on surface environment. Where do you think we should start, Chris, as far as this? Is it an intro to hydrothermal activity broadly, or what's
I think so. Yeah, I absolutely think that. All right, what do you need to have hydrothermal activity? And then we'll just kind of take it from there and run through the features that they have and talk about what do you need to have geysers, and why doesn't Long Valley have true geysers in the Yellowstone sense of the word, or the Iceland sense of the word, right?
So, we'll have maps throughout this, but what do we need? We need hydrothermal. We need those two things, those two words. We need water and we need heat. And we need that heat to be shallow enough to interact really with the groundwater cycle. So the groundwater, we kind of think of groundwater as stuff that's in the near surface. It's in the soil. It percolates down into rocks, into the bedrocks through fractures and things, but it doesn't get down super, super deep. So it's not getting past that brittle ductile transition. We've talked about this a little bit with Basil Teakoff, but it's not getting many kilometers down. It's in the shallow kind of upper couple kilometers of the crust. We think of that as that's at least surface source groundwater or rainwater surface water that's getting down and percolating in. So we need heat that's shallow.
Yeah. The engine is the magma chamber that lies below the Long Valley Caldera proper. That's the engine for the whole thing. And like you said, you have to have this kind of porous and permeable rock. So the snow melt, which is primarily the source of the water, can percolate down to that heat source, get heated up, and then circulate back up toward the surface. So you got to have the engine. You have to have this porous and permeable rock so that you have this kind of free circulation going on.
We've got all of this, activity. What does hot mean? I mean, how hot is hot in the thermal part of this? What are the temperature conditions that we kind of need, do you think?
So, well, that's a complicated answer to that question. So the hot springs, the pools that you get at the surface, and a lot of them are located in the Hot Creek area. And Jesse will show that location of that later on, in the episode, where that is. But some of the hot springs there are in excess of 80 degrees Celsius, and they vary greatly, though. But then you were doing kind of a deep dive into the Casa Diablo geothermal power plant, where they go down a ways, and they're taking water that's 150 to 200 degrees Celsius, and they're using that for electricity. So that's superheated water because it's pressurized at depth. If you go down deeper, it increases, depending on where you are, but it increases rapidly. So
yeah, no, that's right. Depends on where you are. And we'll come back to that. That'll be a big kind of theme next episode. So Chris, what kind of hydrothermal features do we have here in the Long Valley Caldera? Like, what are we looking at? And should we turn to image number 1 that just kind of shows this connection pathway? Because I think this is a bit of a misleading. I want to frame this a minute. You know, the heat engine is magma. Ultimately, it's hot stuff down at depth. It's very rare that any groundwater, surface waters, would actually interact with the magma. So basically, the way to think about this is the magma's heating up the rock around it, and we can have, as we'll talk about in the next episode, we can have fluids, magmatic fluids that are coming out of the magma chamber that work their way up. But we don't like put cold groundwater and put it into the magma chamber and cycle through the magma chamber. It's the magma heats up the rock gets hot, the groundwater interacts with that hot rock and then goes up. So there's not a direct connection between groundwater and magma, which I think is a misconception when it comes to hydrothermal features.
I think so too. Think about it this way, where you have this magma chamber and this hot rock, and then you have this like kind of briny solution on top of that, you know, very, very hot, salty water. That is what's heating the groundwater up above it. That is, you know, and Long Valley has all of the ingredients that it needs for this because it has all kinds of faults and fractures. We talked about that in earlier episodes. That helps the plumbing system. It allows this circulation.
Yeah, and part of it's the caldera forming faults, you know, part of it's the normal faulting that's going on. The extension in this region is creating deep faults that go to depth. So this image that we're showing here, we've got a hot spring up high. We've got this porous rock. This is really key. And porous could mean the rock is permeable. The rock itself is like a sandstone that water can flow through it, or it could mean it has a lot of fractures. So it doesn't necessarily mean that the rock itself, we're kind of using porous loosely, not in the strict geological definition here. It has enough cracks that water can get through it and tap into that heat. But importantly in this diagram, this colored stuff down on the bottom does not mean magma. This means hot water that's maybe coming off the magma chamber, or maybe is just sitting down in this hot crustal package, and the crust is hot because the magma is nearby, but it's not interacting with the magma.
That's right.
Anyway.
Well, so Jesse, I'm going to actually go back and answer your question now in terms of, you know, what do we have hydrothermally? You know, we have hot springs, we have fumaroles.
Should I move to this image real quick, Chris? This
yeah,
one
let's
here
do that. Yeah, okay. Right on. Yep. And you have mud pots, and then you have hydrothermal explosions and not true geysers, and we've already mentioned that before. But most of the hot springs are in the eastern part of Long Valley Caldera, and the reason for that is that there is more water there. It's a lower surface elevation. And so you're closer to that water table there. And then most of the fumaroles, and if you are in the western part of the Long Valley Caldera, because it's a higher surface elevation, and so there's less water available.
Should I just skip ahead? I'm going to skip ahead, Chris, to this image real quick while we're talking about this. This is the caldera, this first frame. And you're saying the western part is broadly higher elevation, eastern part broadly lower elevation. We got a couple rivers going through here. There's a lake down just off this. So you can kind of see this in the first frame of this image to kind of frame what we're talking about, right? So
that's okay. Right. And then if you go back to that image there, yes, that one right there, this just shows availability of water. Higher elevations, there's just less water there. And so the fumaroles, you have water, but it's boiling away before it makes its way to the surface. You get these holes in the ground that just kind of hiss like a tea kettle, if you will.
Yeah.
And it's just
a good way to describe
and they're
it.
really cool.
Oh yeah.
They're you know, I came across some of these on Shasta in Northern California, and you know, you can actually take a water bottle and put some snow in it, and you can melt the snow using the fumaroles nice. Near the top of the volcano. It's a really cool thing, but it's all about water availability. And then somewhere in between, you have these mud pots where you have not enough water to wash away all the mud, but you have too much water so it doesn't boil away.
Sorry, Chris, I just got to turn to this GIF and play this GIF while we're talking about mud pots because this
it's so
is
satisfying.
Just too fun to watch. You keep going, you keep droning on. I'm just going to watch this.
Okay, all right. That's right.
I love watching mud pots. I remember when you took me as a high school student to Yellowstone, and you can just sit at Yellowstone and watch mud pots for hours. I find it's like watching a river or a creek. It's just so calming. Yeah. Anyway.
Yeah, and these are true mud pots at Long Valley Caldera. They're not mud volcanoes. And again, how you get these mud pots, the making of them, the anatomy of them, you have to have quite acidic water involved, because that is the only kind of stuff that's going to really break down the rhyolite and turn it into this clay kind of mixture. So it's this really it's the perfect storm really to create things like this, where you have a water, but not too much water, because then you would just wash away the mud and just be left with a normal hot spring. And so it's just like a perfect amount of water involved to create these things. But again, the importance of it being acidic too, to break down the rhyolite that's in the area and turn it into clay.
I mean, it's a Goldilocks kind of scenario, right, Chris? And so this is what we need for these mud pots. Man, I just can't get over how fun it is to sit here and watch these mud pots.
Yeah.
They are totally fun. Let's move to geysers, because that, I think, is you said that there's fumaroles in Long Valley. There's some mud pots. There's no mud volcanoes, but mud pots. There's hot springs, which we kind of know about and we'll talk about a little bit more. But what about geysers? Let's focus on the geyser aspect. And I'm going to skip ahead here. This is a GIF that we made. It's based on an analogy that you use to teach students when you're in Yellowstone National Park. And I remember you set this up on the boardwalk. You find one of these little boardwalk platforms where students can kind of sit on the benches or sit on the rails, escape the crowds. And you set this up, at least you used to, set something like this up on the boardwalk while we're looking at a geyser, kind of hoping it'll pop off while you're doing this experiment. So walk us through this. What's going on here? How do we get geysers?
So the main difference between a geyser and a hot spring is you need to have this kind of pressure, airtight plumbing system that has usually a kink in the plumbing system, or a narrow constriction. In the case of like Old Faithful, you go down just 22 feet and there's a slot that's only 4 inches wide, that all of that water that's erupting out of Old Faithful has to be squeezed through that narrow slot. And so that's what this is showing, is basically you have this Erlenmeyer flask, and it has a long tube. Like, I think the tube I use is like 3 feet long, but it has a kink at the bottom of it, a narrow constriction there. So you put the tube into the rubber stopper and you put it on the top of the flask, and then you just basically heat it up. As this system heats up, the water is expanding. And so it's pushing it up higher up into this long, skinny tube. And you get to the point where the expansion and maybe some rising bubbles from you're really close to the boiling point here. It's going to push out the water at the top. And what that does then is it diminishes the weight on the water down below. And that pressure, the pressure caused by that weight, is instantly reduced, which allows the water to just flash into steam, and bubbles have to squeeze up through that constriction. They force their way through, pushing more water out, and it just forces the eruption. And so, with geysers, what you need is really 4 things, if you think about it, right? You need to have an abundant supply of groundwater. Long Valley Caldera has that. You need to have a potent heat source. Long Valley Caldera has that. You need to have this plumbing system, faults and fractures, porous, permeable rock that we talked about before. Long Valley has that. And then you need to have this kink or constrictions within that. And this is what Long Valley Caldera does not have. So it doesn't have true geysers in the textbook sense of the word. So let's talk about that, Jesse. Why doesn't Long Valley have that constriction in the plumbing system? What's going on with that?
Yeah, so I mean, it's an interesting question, right? Because this constriction thing, and there's differences when you go to Yellowstone. There's differences as you move across the park, across the caldera, in the proportion of geysers, largely due to the groundwater chemistry and how these constrictions are really being formed. So as you said, you need to dissolve the silica from the rhyolite. So we need to dissolve this stuff, pull it into solution. When you have the silica in solution, then you can kind of dump it out and create this sinter. It's, SiO2 kind of pseudomorphs and different varieties of that. But you dump this stuff out and create these constrictions by precipitation, and especially when you're fluctuating the temperatures, when you're fluctuating the groundwater chemistry, when you're flashing to steam, there's a lot of chemistry that happens in those processes. So you can build up these constrictions. You can also blow them out and damage. Like, geysers are not stagnant. Geysers get they cough out these little constrictions, right? They break themselves apart.
They can turn themselves right into hot springs.
Yeah, exactly. And then hot springs can kind of turn themselves into geysers with enough time and precipitation. So this really dynamic system that's based on the fluid chemistry, this really high temperature, really reactive fluid chemistry that's going on. And Yellowstone has this in spades. Long Valley, not so much. And the reasons are, well, I don't know, Chris. I'm curious. I could, a couple hypotheses or a couple random thoughts come to mind here, and I'd be curious what your thoughts are. Like, why does Long Valley not have this? First one that comes to mind for me is the timescales. So Long Valley, we talked about this. There's several large eruptions, but really kind of in one pulsed event. They're big, but they're in the Yellowstone category of eruptions. But Yellowstone's had 3 in this category over a couple million years, whereas Long Valley had 1 broadly, 760,000 years ago. So it's a bit of there's a difference in the amount of rhyolite and the locational spread, like how well distributed these things are. I mean, is that something that you think might be at play here in the differences between Yellowstone and Long Valley?
Absolutely, for sure. The other thing too, Jesse, is that the rocks here are more fractured. They're more busted up, which allows water to come and go more freely, and you can't have that with geysers. Water has to be contained within this system. It's called something called exchange of function, where water can kind of come and go. That's what's happening in Long Valley Caldera. So it's just too permeable, too fractured, too broken up. The plumbing system is just different. One thing
I don't know this offhand. Is there a rainfall difference, like a groundwater supply difference between Yellowstone and Long Valley area? I mean, they're both kind of they get a rain shadow effect, and the Sierras, build up a huge snowpack that kind of, I guess, melts off at least to the east, towards the east into Long Valley as well. So I'd be surprised if there was a difference. Do you know if there is a rainfall total?
I really don't. I mean, they get a lot of snow melt from Mammoth Mountain, the ski resort area there in Long Valley. So I really don't know, though. I don't have an answer to that question. I just, Long Valley doesn't have true geysers like Iceland and Yellowstone does, but it does have a really active hydrothermal system. And part of that is these explosions that happen, these hydrothermal explosions.
Man, Chris, there's some, it's, well, we'll talk about it a little bit more, but it's dangerous, and it's dangerous in Yellowstone too, but it's dangerous here in the unpredictability of, these warm water creeks that can turn boiling instantaneously, effectively, with little eruptions or regurgitations of hot water, extremely hot water into the stream bed or into the area. So yeah, it's a very dynamic hydrothermal system. And as we'll talk about, that hydrothermal system probably has something to do with the inflation that's going on, and so this is like a breathing in and out area because of the water, and it's sensitive to snowpack, and it's sensitive to all these things. So
that's right. So Jesse, can you go down to the next?
Yeah.
There we go. There, that one. I think this just does a good job of explaining the difference between a hot spring and a geyser. The hot spring just has this free flow of water to the surface. It's not restricted, so there's no really pressure buildup that happens with that. With geysers, you just need to have that, and there's just so many avenues for water to come and go within the Long Valley plumbing system. But just it's harder to create. You need this perfect recipe in order to create geysers, for sure.
Yeah, you really need these constrictions, and it does. Long Valley does have these what you described as hydrothermal explosions, whereas geysers we think of kind of a lot more regularity to them, and probably not as large, not as potentially damaging. But hydrothermal explosions do occur, and these are most often related to a larger hydrothermal system down below, somewhere water has gotten trapped and then undergoes the geyser, the same exact first boiling principle that you talked about, Chris, where you kind of decrease the pressure and boom, it blows. Those are kind of one and done type explosions. Yellowstone has a long history of these. Long Valley also has these. There's one in 2006 in Hot Creek that we're going to tell the story behind here, but those do occur. They're just much more rare and punctuated. Is that a fair way to explain the difference?
Absolutely. The Hot Creek thing that you just alluded to, the most recent hydrothermal explosion was in
image real quick too, so that we're just showing it. Yeah.
The last one was in 2006. So they closed the area and they have not reopened it. Well, I mean, you can go visit, you can stay on the boardwalks and so on like this, but you're not allowed anymore to enter the water. It was I guess maybe to think of an analogy, it was a lot like the Firehole River in Yellowstone, where you're able to go into the Firehole River,
sure.
and you get these areas where you have this really pleasantly warm water, where you have this mixture between cold stream and runoff from hot springs and so on. They don't allow that anymore in Hot Creek because of the hydrothermal explosions.
There's a very valid reason for this. We'll touch on some of the aspects of this, but yeah, because as we talked about before, I've seen photos taken 5 seconds apart where the water's like warm, pleasant, and then the water's scalding, incredibly scalding, really deadly water, and it's boiling up out of the water, out of the stream, and you're just like, if you get caught in that, it's really rough. So there's a reason that it's been closed off. This, again, there's a lot of connections here between this episode and the next episode we'll talk about, but this hydrothermal activity, there's uplift going on in this region. And whenever we're in a volcanic area, and especially like one that is, produced super eruptions before, or close to really big eruptions before, uplift is always piques the interest, let's say, of the geologists and the people around it, because it's a sign of activity. We don't know what the activity might mean, but this hydrothermal activity is related to the uplift. We get these seismic swarms, gas emissions, all sorts of stuff, and it could be, we need to work to understand that. That's what next episode is really about. But these are all
so we're not going to touch on that right now then, Jess?
Well, no, we can, we can briefly touch on this, but I just want to point out that these are signs of, these are like potential warning signs, right? If you're a volcanologist working on the volcanic hazards program for the U.S. Geological Survey, these are things you perk up, like you pay attention to these. And so all these things are kind of going on in this area, and it's a sign of this activity. There's something happening. Stuff's moving down at depth. Whether it's a prelude to an eruption or not is an interesting question,
right.
But yeah.
Two options, right? With this, because this is a living, breathing system. Obviously, we've had a lot of uplift. You have some deflation and inflation and so on. It's kind of like taking a deep breath and your chest heaving. If you're laying on your back, your chest heaves up and down. It's either probably injections of magma or really dramatic changes in hydrothermal activity. That's why this is being monitored, because that's a really important question to answer.
Yeah,
right.
Totally. And that's the whole next episode is what's going on, various hypotheses, various ways to tease these apart. And I think focusing in on how the vast array of tools in the geologist or volcanologist toolkit to assess that question with different volcanoes and how different they are. Each volcano is a snowflake, as Diana Roman says, and Long Valley is a particularly interesting snowflake. So, Chris, I just want to highlight this is the Hot Creek area, and you can see this fence, and this is a dynamically changing place. There's a new pool here that's opened up since the fence was in place, and so you can kind of obviously you can get a sense for, if you zoom in, the fence is in the pool now. You get a sense for why this might be fenced off, right? Just by looking at the dynamic changing landscape, and Yellowstone shows this dynamism as well.
That's right. And you get the same thing, right? Yellowstone is really well known for having these, sinter mats. Silica is dissolved out of the rhyolite, and then when it comes up to the surface at lower pressures and temperature changes, then as it cools off, it precipitates this silica mat that we call sinter. And you get the same thing in Long Valley Caldera too, especially around the Hot Creek area.
Yeah,
beautiful.
It makes for beautiful water, beautiful hot springs. They make them really, really pretty. Chris, all right, well, let's move on. I want you to tell this story of the tree kill areas. And so, it's a really interesting story. It's really sad in some ways, but informative and telling about the dynamic aspect to these areas and how we, in the modern sense, kind of detect and sense and think about these systems, the interplay between volcano, hydrothermal systems sitting on top of it, and humans living on the surface. So I'm going to sit back here. I'm going to get down to
don't get too comfortable, because I'm going to toss it back to you, because I'm going to let you talk about Casa Diablo, just a little bit about the geothermal area and how that fits into this whole thing. So Long Valley Caldera has some of the highest carbon dioxide flux of anywhere in the U.S. So dramatic changes in CO2 emissions. And what happens is carbon dioxide is a heavy gas. It's colorless, it's odorless. And so if you have these sudden burps of carbon dioxide, it's just going to flow down into low areas and it's going to sit there. and it can then suffocate especially if it's really rich in the soil. It'll kill things. It'll kill trees and the foliage on the surface, and that's exactly what happened. So we're talking about the Mammoth Mountain tree kill area. This was first noticed in the 1990s, and it's it's a massive area where the south side of Mammoth Mountain, over 170 acres, carbon dioxide levels, Jesse, were over 90% in the soil.
Wow.
The
soil gas was
in the pore space. That's right.
Yeah. I mean, it's amazing.
Yeah. And so it just caused these trees to just rapidly die. And you can see this in this image here. And actually, it looks like these trees also have soaked up some silica through capillary action, which is why they almost look petrified at the bottom of it too. You see this a lot. You see this a lot in Yellowstone as well. And so I want to talk more later on about what happened in 2006 and the deaths that were involved with that. But Jesse, first, what about the Casa Diablo geothermal area?
Yeah, I mean, I think if I just go back, let me find this image. I'll just go back to this location map and just highlight where this is, south side of the Resurgent Dome within the caldera here. This is a geothermal plant, and I'll skip ahead now to an image of this. This is a bit of an older image now, but this is a geothermal plant. So this is a geothermal plant that's producing electricity. It's got 60 megawatt of geothermal, four different power plants. First was built in 1984. The most recent just came out a couple years ago. 60 megawatts is a significant power source and a power supply. It pales in comparison to other power plants. I mean, one of the largest ones is the Grand Coulee Dam, which has 10 times, or actually 100 times, 100 times the power generation capabilities of this geothermal plant. But for me, it's an interesting exercise. Geothermal is one of the really hot fields for subsurface geology for future energy supplies. It has a lot of promise and a lot of potential downsides. Most of them are engineering downsides. And as we kind of talked about some of these, like if you're trying to long-term get heat out of rocks, you got to have the ability to extract that heat. Heat moves very slowly through rocks. It conducts very slowly through rocks. So you can't just pull heat out and expect the heat energy to move for the rocks. You got to have a well-fractured network of rocks that you can kind of pass fluids through, and you can extract that heat for a long time very consistently. There's some massive benefits to geothermal energy, and it's a kind of a huge resource when done well in the right areas. And I think this is probably one of the examples you can just see by the longevity. I mean, since 1984, and then new units coming online recently. So it's a very interesting exercise, and just again highlights, if you do a map of geothermal systems online in the United States, you're basically finding hot areas in the US, right? You're finding where is there shallow magmatism, relatively shallow, relatively recent magmatism, where is there hydrothermal systems, where are there hot springs. Usually there's going to be, if there's a geothermal system somewhere, usually there's a hot spring nearby, because it just tells you the temperature gradient in that area is high. So you get hot quick when you don't have to drill down 12 kilometers to get hot. You can do it shallower. So anyway, that's all I have to say about that, but I think it kind of relates to this whole process, these systems. So back to the CO2, right? Is that where we're focusing on? So I'll go back to this tree kill.
So I was talking about the biggest tree kill area, but there were other smaller tree kills that were noticed. But it started in 1990, and it all started because there was a park ranger that was stationed in a remote cabin near Horseshoe Lake, which is known for geothermal activity. And he started to he was dizzy. He has some nauseousness and headaches and so on. And he says, he was really close to, not really making it out of there. He suspected gas from nearby vents and so on, but it wasn't. This is what kind of spurned the CO2 studies that's going on in the area, was this 1990 event. But it wasn't, Jesse, this is crazy to me, 16 years later, 2006, when 3 ski patrollers died due to asphyxiation from carbon dioxide. And they
in the
were
same area,
working,
in the same
they were working. This was in April. They were working near a fumarole, and this fumarole had been known, right? I mean, they actually had it fenced off, but this area will just get pounded with snow events, and so they sometimes had a hard time locating where the fumarole was.
Sure.
Because
Yeah.
it would just get buried before the fumarole was able to melt out the hole again. So one of these ski patrollers fell in, another one went after him, and another one went after him, and all three of them succumbed to it. A fourth one was, pulled back in time, and so it resulted in 3 fatalities. Really tragic. But
so this was I just want to kind of paint the visual, or be clear about the visual here. This was a fumarole vent that was high concentration of CO2, kind of a restricted area, and it wasn't just like
it was,
skiing. It wasn't just like kind of walking along and get asphyxiated. Like, it's not like you walked past these trees and toppled over from asphyxiation, but kind of fell in a cavity that was fumarole induced thing. Yeah, okay, gotcha.
Yeah, and same thing with the cabin. The carbon dioxide seeped out of the soil and just filled the cabin up with carbon dioxide.
Right, of course.
But it wasn't until 16 years after the 1990 event with the cabin and the Ranger where these fatalities happened, where the real extent of the carbon dioxide hazard then became clear. It's just I don't know. It's amazing,
so Chris,
right? I mean, carbon dioxide is,
A question for you, to kind of come back to our comparisons with Yellowstone. Are there locations in Yellowstone where there are high CO2, these kind of CO2 numbers, or this kind of tree kill due to CO2 coming out of the ground and less due to I know that there's areas where trees die because, a new hydrothermal system kind of starts to open up under them and they kind of die by heat and poisoning of the groundwater. I don't remember that being CO2 outgassing. But is that
no,
true or not?
I don't know. I have never heard of
it.
This thing. I've not heard of anything like this in Yellowstone National Park, that's curious, isn't it? Why is there so much carbon dioxide flux associated with Long Valley Caldera? Magma has lots of gas dissolved in it. The primary gas is water vapor. The second most abundant gas is carbon dioxide. And then it's followed by lesser sulfur dioxide and H2S, the rotten egg smell, which is like we humans, our noses are really adept at detecting hydrogen sulfide.
Yeah, it's one of your favorite aspects about being a human, I think, Chris, is that you get to go into Yellowstone, drive your big yellow bus, and stop there and open the door and go, that sulfur smell.
That's right. I love it.
You love it.
So I don't know. The answer to that question. I've never heard of it.
But you haven't heard of it, at least. I mean, if it was a very prevalent phenomenon, I'm guessing you would have heard of it.
I would think so, yes.
That's probably a telling thing. Well, we can ask somebody. We can ask Mike Pauland or somebody else we've talked to about Yellowstone on podcast. But, yeah, I think it's really interesting. It's a very interesting juxtaposition. And, again, just highlights each volcano is a little snowflake, right? There's really high-level differences between Yellowstone and Long Valley Caldera, even though they had there are similar categories of eruption, but very, very big dramatic differences anywhere from where the melting is coming from to perhaps even what the magma chambers are doing today. Big differences there. So,
and you can Google image that fumarole. We didn't put it on here because we couldn't find a public domain one, and we didn't want to infringe anybody's copyright or anything like that. But you can see that fenced off area with the big hole in the snowpack and so on, where this tragedy happened.
Yeah.
So
So Chris, just to end here, there's a lot, or to kind of summarize maybe, there's a lot of differences. There's a lot of similarities between hydrothermally rich areas, and Long Valley has a particular set of things. It has it doesn't have geysers. It has hydrothermal eruptions occasionally, far fewer geysers than Yellowstone, but who has as many geysers as Yellowstone, right? Not many places are even close to that. Does have hot springs, does have some fumaroles, as we've touched on, and a lot of it has to do with differences in how the groundwater circulates through, whether it gets restricted or not, what the groundwater chemistry coming in is, how much rhyolite and obsidian is around to be accessed by the groundwater at depth, and some, what the surrounding rocks are. How does the water get there, and so you've got snow melt up in the Sierras as it percolates down, it's interacting with granites. Where in Yellowstone, at least in the Mammoth side, you have the same kind of phenomenon, but that water goes down, it's interacting with carbonates and sandstones. It lends up with a very different groundwater geochemistry. And so the intricacies matter here. The details, the weeds matter and affect the surface hydrothermal system a lot.
One final thought too, Jesse, is Long Valley has almost everything you need to have in order to have geysers. I'm shocked, Jesse, that there isn't one. There's not one true geyser in this really large area. I just wonder if there have been in the past, and then, like you said, they erupt and they cough out their center lining and just become go back to being a hot spring.
Yeah,
I don't know.
That's a good point. Whether hot springs become geysers briefly, but not for the long duration that Yellowstone geysers end up behaving. So, yeah, interesting questions, interesting features of another really interesting comparison between the two places. So. What do you think? Is that a wrap on this one?
I think so. That's a wrap.
Okay, next episode we're talking about what's going down at depth and how do we know? How do we test it? How do we detect it? How do we sense these things? It's an interesting conversation, intimately related to the hydrothermal features here. You can follow us on all the social medias. We're at Planet Geocast. You can get content like this in addition to other audiobooks on the Yellowstone National Park. We have 12 chapters in gruesome detail on Yellowstone National Park geology with images like we're showing you here on our
gruesome
CampGeo.
Detail, huh?
Gruesome detail. We're in the weeds. It's gruesome down there. And our CampGeo mobile app, first link in your show notes. You can download that or just search CampGeo in your mobile app store on your mobile device. Send us an email, plantgeocast@gmail.com.
Cheers.
Peace.